Hello, my name is Alpesh. Me and my classmate Tofi, we are going to present a PPT on thermal analysis of U2-based solar ETC with different flow conditioning inserts. Basically, solar evacuated collector has multiple glass tubes, and inside that glass tube, U-tube pipe is kept. Solar radiation from the sun is concentrated on these U-tubes, and working fluid is circulated inside the tube. As fluid travels from one point to another point, temperature inside the fluid increases. In order to prevent the heat loss due to conduction and convection, vacuum between glass tube and U-tube is maintained. Generally, plain U-tubes are used inside these types of devices and they are moderately efficient. But there is a room for improvement. Hence, our goal for this study is to try different types of inserts and determine its impact on performance. We will also try different types of material for YouTube such as copper, aluminum and brass. Optimizing operating parameter for maximum performance is also a part of our study. As there is no actual setup, we are going to evaluate result using ANSYS 2022 R2 platform for thermal analysis and Autodesk Inventor for 3D modeling. So this is the geometrical description of 3D model. We are going to study three types of flow conditioning inserts with 2, 3 and 4 internal fins as shown in figure. Continuity equation, momentum equation for x, y and z direction and an energy equation. ANSYS Fluent Solver uses these governing equation to examine the 3D model of U2BTC. Unstructured tetrahedral mesh is used as it guarantees the best discretization of U2 model. Finer mesh sizes are used at the working fluid zone over the U2 bend and along the working fluid boundary layer as shown in figure. Reduced temperature difference, mean fluid temperature, thermal efficiency, useful heat gain per unit area, and heat gain. These are the equations are used to evaluate the performance of our study. The operating parameter focused in our study are material effect, mass flow rate effect, inlet working fluid temperature, and the effect of solar irradiation. Material effect. The temperature difference of working fluid between the inlet and outlet of the collector is used to evaluate the performance. Table 1 summarizes the material property of U-tube materials. Different U-tube materials such as copper, aluminum, and brass are used in the study and their performance is shown in figure 10. The change in fluid temperature of water for copper is 13.1 Kelvin, which is the highest compared to other two at a constant mass flow rate of 0.001 kg per second. From the graph, it is clear that thermal efficiency of copper is highest. Hence, copper is taken as a material for U-tube in this study. The influence of mass flow rate on the collector net temperature gain is illustrated in figure number 11 and 12. In this present study, the mass flow rate of 0.001 kg per second, 0.003 kg per second, and 0.005 kg per second are used. Figure 11, it shows that the change in fluid working temperature for 0.001 kilogram per second is highest compared to other two. This is because for given inlet condition, the net temperature gain decreases significantly with increase in mass flow rate. You may ask why. It is because the working fluid inside the U-tube has less time to interact with the wall surface when it is flowing at a higher mass flow rate. Subsequently, the thermal boundary layer thickness between the working fluid and U-tube wall increases. Hence, the outlet working temperature is found to be low at a higher flow rate. It is noticed that with the decrease in flow rate from 0.005 kg per second to 0.001 kg per second, the temperature difference between working fluid at inlet and outlet increased by 5.3 Kelvin. Effect of inlet working fluid temperature. Figure 13 shows that the net temperature gain achievable at different inlet water temperature. It is observed that the net temperature gain decreases with increase in the working fluid temperature. This phenomenon is very obvious. As the inlet temperature increases, the heat absorption capacity of working fluid decreases. This may also due to the decrease in overall heat transfer rate between U-tube surface and the working fluid with the higher net temperature. From figure 13, we can say that the increase in working fluid inlet temperature from 300 Kelvin to 313 Kelvin, the net temperature gain reduces from 11.1 Kelvin to 7.2 Kelvin. This analysis illustrates that heat transfer rate are slower at higher working fluid inlet temperature compared to working fluid temperature at a lower inlet temperature. Solar irradiation effect. The variation of solar irradiation with net temperature gain is illustrated in figure 13. To investigate the effect of solar irradiation with net temperature gain, solar irradiation was varied from 350 watts per meter square to 836 watt per meter square with fixed operating condition. From figure, it is clear that increase in solar intensity result in increase in net temperature gain. It is because the solar irradiation increases, the heat transfer rate increases from inner glass surface to the copper U2. It is also found that the solar irradiation increases from 350 watt per meter square to 836 watt per meter square. The net temperature gain between the inlet and outlet temperature rises by approximately 11.2 Kelvin. After performing all this analysis, optimum characteristics for the studies are as followed. The material for U2 is copper. Water is considered as the working fluid. Inlet working fluid temperature is 300 Kelvin. The mass flow rate of fluid is kept as 0.001 kg per second. and the solar irradiation is 836 watt per meter square.
And moving on to the temperature distribution of working fluid inside the U-tube along with flow direction, which is shown in the figure. It can be perceived that water with a lower temperature goes into the inlet of U-tube, flows along the tube towards the outlet. The figure reveals that the inlet temperature is 300 Kelvin and has been increased to 313.1 Kelvin at outlet temperature due to the solar radiation. And the pressure drop along the U-tube length, it is observed that the pressure drops by 0.54 kilopascal for the optimum condition. Forced convection flow is considered in the present study. It is important to predict variance in pressure drop along the U-tube length by retaining the rest of the operational parameters as constant. And the figure represents a contour plot of the pressure drop. It is observed that with the flow rate progress towards the end, pressure drop increases. This is because the flow rate increases, the dynamic pressure loss is caused due to the change in the direction of flow along the U-bend and frictional loss. It is also observed that the pressure drops by 0.54 kilopascal as I mentioned earlier. The results of proposed flow conditioning inserts is that the analysis is accomplished with optimum operating condition and mass flow rate of 0.001 kilogram per second. In case of plain tube inserts, the net temperature gain is obtained as 10.3 Kelvin for the two internal fin cases, and the net temperature gain obtained as 3.1 Kelvin for a useful heat gain of almost 395 watt per meter square for the triple fin case. At the same operating conditions, the net temperature gain is 13.1 Kelvin. And for the four internal fin cases, at similar operating conditions, the net temperature gain is 4.6 with useful heat gain of 474.5 watt per meter square. The triple fin based U-tube EDC presents an increased temperature difference of 2.8 Kelvin and 10% higher thermal efficiency compared to plain copper based U-tube. But how does that happen? There are two reasons for that. First being generally when the tube walls heat the fluid in the vicinity of the tube walls is heated up first and the temperature gradient is formed between the fluid near the wall and the fluid at the core region, and it forms a boundary layer we studied in fluid mechanics and advanced thermodynamics. So conversely, the triple fin U-tube design disturbs the original thermal velocity boundary layer pattern, and hence heat transfer rate is more. Second reason is that the triple fin decreases the cross-sectional area of the flow passage, leading to a stronger turbulence intensity that helps to provide a larger interaction area of the fluid to the tube wall, and hence it enhances the heat transfer. The results of all fin U-tube are illustrated in 17, 18, and 19. And the next question is that what if we increase the number of fins to 5, 6, 7, 8, and all that? So does the efficiency of the U-tube increase? The answer is no. It is observed from figure 19 that the number of fins is directly proportional to the pressure drop inside the tube. So as the number of fins increases, it obstructs the fluid flow. Hence, the mass flow rate of the fluid decreases, resulting into the pressure drop. This indicates that there are significant restraints in the designs with several extended fins. Typically, the pressure drop varies from 0.3 kilopascal to 0.8 kilopascal. And in the conclusion, in this study, we have investigated the difference in inlet temperature from 300 Kelvin to 313 Kelvin, the mass flow rate from 0.001 to 0.005 kilogram per second, and solar irradiation from 350 to 836 watt per meter square. From the parametric study, it is found that the optimum condition of the inlet water temperature is 300 Kelvin, mass flow rate of 0.001 kilogram per second, and solar irradiation of 836 watt per meter square. The net temperature gain decreased with an increase in the mass fluid flow rate of the working fluid. It was observed that by increasing the flow rate from 0.001 to 0.005 kilogram per second, the thermal efficiency is increased from 33% to 53%. All the studied flow condition inserts enhanced thermal performance. It was found that the maximum thermal efficiency enhanced about 10%, and it could be improved higher solar intensities. For the present study, maximum thermal efficiency of the solar U-tube evacuated tube collector is found to be 62%. Triple fin based model provides better thermal performance than all presented models with temperature gain of 13.1 Kelvin. And here's a summary. And thank you.
Thank you.